Republic of Korea. And he will present to us his work on strategies of improving the stability of Faradic electrodes. So the floor is yours.
Thank you for the introduction. My name is Jaehan from Hongik University, and I'm delighted to introduce my presentation in BDINE conference. Today's my topic is strategies of improving the stability of Faradic electrodes, and this presentation will take about 15 minutes. This page shows the content of my presentation, and I divide my talk into two parts. As you know, lithium is one of rare metal, and it is widely used for science and technology. Especially these days, the demand for lithium has been greatly increasing due to the use of rechargeable batteries. Then where are lithium located? Lithium resource located. This figure shows the lithium resource, and South America holds 75% of the non-global lithium river space. And this page shows the conventional lithium recovery process from brine that called lime soda evaporation. And this process including more than 1 year evaporation process for concentration of lithium. And also water is essential resource for our life, such as washing, drinking, and farming. However, above 75% of water is saline water, so it is required to desalinate for sustainable freshwater supply. And there are two main desalination technology, conventional desalination technology. One is thermal process, and another is membrane process. However, requiring complex process and high operation cost are the limitation of conventional conventional ion separation process. And also, energy still require very high energy. Even RO is considered as the most energy efficient ion separation process. To overcome this limitation, electrochemical ion separation using Faradic electrodes have been developed for resource recovery and desalination because of its no chemical usage and simple to operate reversibly. However, pro-cyclic stability of Faradic electrode is a critical issue for commercial usage, especially lithium manganese oxide and pro-ceramic broad materials. The stability of lithium manganese oxide and pro-ceramic electrode shows below 80% after 20 cycles. So it is required to improve the stability for commercial usage. To improve the stability of Faradic electrode, I try to find some strategies from battery technology. One is state of charge control, and this is one of battery management system in hybrid vehicle, electric vehicle, battery, and energy storage system. And the state of charge control is the method for minimize the damage to battery electrodes by controlling the operation voltage range. And it is possible to enhancing battery cycle life by using this SOC control method. Another strategy is for improving battery technology is surface protecting, especially using some polymers on the surface of the battery electrode. It is possible to minimize volume exchange in the electrode and reducing size reaction. And in part one, I'll talk about state of charge control for lithium recovery. As you know, lithium manganese oxide is well-known material for lithium ion selective absorbent because of its very narrow crystalline structure. So it has a widely used for lithium-ion selective material. And also, this material has electrical redox behavior, so it is possible to use for electrochemical ion separation process. However, mangan ion dissolution during charging and discharging is a limitation of stability. This page shows the material method of galvanized charge discharging at different SOC control level. I use positive electrode for lithium manganese oxide and negative electrode for silver chloride electrode. And SOC is controlled by voltage cut operation. And this page shows the experimental method of lithium recovery. And lithium, I used lithium manganese for positive electrode and silver chloride for negative electrode. And the lithium recovery is there are two steps for lithium recovery. First step is discharging step for lithium recovery, selective recovery from brine, and then the solution is changed and charge the cell. Then the captured lithium ion is released into reservoir solution. And also this lithium recovery is also controlled controlled by SOC level, and I compare the energy consumption and lithium ion selectivity. And this page shows the result of cycling stability data. And upper figure shows the cycling result of 100 SOC. It means that fully charging and discharging operation. And as you can see from the capacity retention, the capacity is greatly reduced during 20 cycles, and 60% of capacity retention after 50 cycles. And lower figure shows the cycling result of 60% SOC control. And as you can see from the capacity retention data, the capacity is gradually reduced and remain 85.4% capacity retention after 50 cycles. And right figure shows the cycling stability of different current rate. And as you can see from this figure, 60% SOC control remain higher capacity retention at different current operation compared 100 SOC control. And this page shows the XRD patterns of lithium manganese oxide before and after cycles for different SOC level. And we can check the structural changes of material by checking the 511 and 440 fix. And the fix are shifted more by the increase of the SOC level. It means that the lower SOC control showing the similar result of freestanding electrode, and it means that the damage of electrode is minimized. And this page shows the result of lithium recovery test. Upper figure shows the selectivity of lithium recovery. As you can see from this figure, the selectivity of both of control methods show a great lithium ion selectivity. It means that SOC does not greatly affect of selectivity of ion, and we can calculate the energy consumption by time versus voltage data. And from this data, the energy consumption of 60% SOC shows 5.1 watt-hour for one more of lithium recovery, and you can check the increase the energy efficiency is caused by the side reaction, and IR drop are reduced at 60% SOC control. Now that covered SOC control for return recovery, let's move on to surface coating for desalination battery. Prussian blue is a well-known material for absorbent, and also it has it shows electrochemical performance of redox, well redox reaction. So it is widely used for battery technologies such as sodium-ion battery. However, dissolution of the Prussian blue after cycling is the problem for electrochemical usage. This page shows the experimental method of our research, and for nappion coating, we used 117 nappion solution, and the surface is coated by draft casting method. And this figure shows the cell design of a desalination battery, and I used two Prussian blue analog electrodes coated by nappion, and there is an anion exchange membrane between two electrodes. And this desalination tests were conducted with 500 millimole sodium chloride solution. And this page shows the morphology of the electrodes by SCM, and upper figure shows the pristine Prussian blue analog electrodes, and lower figure shows the nappion coated electrode. As you can see from this pristine electrode image, the Prussian blue analog particles, the size of Prussian blue analog particle is approximately 1 to 5 micrometer, and the coated electrode have clean and smooth surface. It means that nappion polymer is well covered on the surface of the electrode. And from the side view, the polymer, the thickness of nappion polymer is approximately 5 micrometer. And this page shows the electrochemical performance of coated and pristine Prussian blue analog electrodes. And from the cycle potentiometry data, sorry, the reaction peak of pristine and nappion coated shows similar reaction peaks. And from galvanostatic charge resistance data, the capacity of nappion coated and pristine electrode shows a similar capacity. This result shows that nappion layer does not significantly affect sodium ion diffusion and capacity. And this page shows the cycling performance of pristine and nappion coated electrode. As you can see from offside of figure, Prussian nappion coated Prussian blue shows 94% of the initial capacity with approximately 100 chromic efficiency. On the other hand, pristine electrode shows pristine electrode is 90% of capacity show after 100 cycle with 93% of chromic efficiency. And lower figure shows the image of electrode and space of the pristine cell and nappion coated electrode after 100 cycle. As you can see from this figure, in the cell containing nappion coated electrode was maintained for 100 cycle with no color changes observed in the spacer. And this page shows the result of desalination performance. And left figure shows the result from a 1 hour charging operation. And from the result, the charge efficiency was 89%, and the energy calculated energy consumption is 506 kilojoules per mole. This is a much higher value than using non-coated pristine electrode material. And we also check the maximum capacity by operation of, of the voltage between 0.05 to 0.85 volt, and salt removal efficiency was 78%, and the maximum salt removal capacity was 72 million per liter. This is much higher value than using non-coated electrode that was 60 million per gram.
Have a MCDI, the black color.
This page shows a conclusion of my presentation. I introduced two strategies of enhancing the stability of Faradic electrodes. One is operation control by adjusting state of charge, and the other is surface protecting by coating napio. Before end of my presentation, I appreciate my supervisor during PhD candidate, Prof Jaehan, and my co-author, Dr. Hwaju and Jaehan, and my graduate student for showing this result. And this is the end of my presentation, and thank you for your attention.
Thank you, Professor Lee. It was a very nice talk. So, is there any questions? Julio?
Very nice presentation. I'm curious, when you are testing the Prussian blue electrodes, you are doing a quite high concentration, it's almost 500 millimolar,
yes,
like
sure.
seawater.
Yeah,
but
almost the seawater.
Have you tried to decrease the concentration to brackish water like 40 millimolar, 20 millimolar, and see how is the stability?
Actually, I didn't test it in brackish water. I expected it is also improve the stability by using this coated material.
Yeah, I think probably it's better, but it's true. The experience that we have is when we decrease the concentration, the problems of stability are even worse. So it will be great if you could 40%. Test that and tell me how much is improving. We are really working on that, and we don't have yet a good strategy to stabilize the electrodes.
Thank you.
It's
40%. Thank you. So, there are other questions? Yeah, one there.
Thank you for your talk. I also have a question on the Prussian blue stability side.
Combined with the nanomaterial,
usually Prussian blue often used for the selective recovery of ammonium or potassium. And once you have Nafion also have 20% of capacity increase when you have Nafion coated. So do you think there still have selectivity when you, even if you coated the Nafion, or do you think selectivity will decrease with the coating?
I think the increase of the capacity is caused by increase the charge efficiency by reducing side reaction, and so maybe the capacity increase is, I'm not sure, but it is possible maybe, but I think I should be checked about this. Yeah.
Okay. Thank you for the discussion. I think we'll conclude here. So let's give Professor Lee a hand. And that brings me to the final speaker of the session, which is Professor Jianfang Su from Tamkang University, Taiwan. And you are going to entertain us on a talk on a highly porous copper catalyst for electrochemical nitrate reduction towards ammonia synthesis in water. So please, Professor.
Okay, thanks, Professor Mo, for the introduction. And it is a great pleasure having this opportunity to share my research with